this needs cleverer testing than we've got. So up they go to Cornell University. Now at Cornell at that time, they said that they got this amazing new equipment, and this equipment could test anything that you'd got down to 3 to 5 parts per billion. So they put it on their machines, and they came back and they said it's iron and silica and aluminum. They said, well, it can't be. None of those things disappear in a blaze of white light. No, I mean, none of them have these properties. There must be more to it than that. So they tested them again, and they discovered that actually the reading that they were getting was just a little impurity at the front level. It was reaching the boiling point of these particular substances. And once they got rid of them, and they were less than 1% of the whole, once they got rid of them and tested 99% plus of the sample, they said, we can tell you exactly what you've got. Pure nothing. You have nothing that our machine will read. It will not acknowledge that there's anything on there being tested. It's nothing. So they said, okay, we'll try arc emission spectroscopy. Very, very simple process. 2 electrodes. The bottom one has a cup in it. You place your sample in the bottom cup. You bring the other one down and you strike an arc. That arc heats up and ionizes what's in the sample, and one by one, as it reaches the boiling temperatures of each of the constituent elements, it will read them off and tell you what's there. So if, for example, you put a motor car engine in there, its first reading would tell you it was water, because it was reading the cooling system. When the water had all boiled away, it would then tell you it was metal. So that's the way it works. So anyway, they put the stuff in there, and the same thing happened. They said it was iron, silica, and aluminum, and that was it. Nothing was recognizing it. It was not listed. It was totally unknown to science, this strange white material that would disappear from vision. Well, then the Russians came along. The Soviet Academy of Sciences. We're now into the 1980s, well into the 1980s, and the Russians said, we've been telling you guys in the West for the longest time, you really haven't got much of a clue when it comes to analyzing materials. Your electrodes burn away before you can reach the boiling temperature of some of your materials. Carbon has a lower boiling temperature. These electrodes are made of carbon. They're burning away before whatever it is has heated up enough. So it's not reading it. Russians said you need to burn this in an arc for 300 seconds, not 15, which was common in the West. 300, 5 minutes. So they go back to base and they put the material in, and it begins. Within 15 seconds, iron, silica, aluminum. They all expected that, and then it's nothing. But the arc now is carrying on burning, whereas the Western style one stopped. And suddenly, at 70 seconds, it says it's palladium. After palladium reads platinum. After that, as the various boiling temperatures were reached, came ruthenium, rhodium, iridium, and at 220 seconds, osmium. Every one of the platinum group metals was in this substance. It was them. It just wasn't showing up at them as them in a metallic way. And in fact, when they worked out the content of these soil samples, it was discovered that per ounces of substance per ton of soil, they had 7,500 times more platinum in every ton of their soil than they were getting from every ton in the best platinum mine in South Africa. But it wasn't metal. You couldn't make jewelry with it. Suddenly Hudson discovered that General Electric up in Massachusetts were looking at a new sort of fuel cell technology. And he said, look, I've got this stuff here, and it says in your literature that you're using rhodium and iridium and these platinum group metals for fuel cells. Your reports say that you're experiencing very strange phenomenon. You're experiencing blazing white lights and explosions and disappearing tricks and things. And they said, yeah. And he said, well, I've got some stuff that does that. And they said, yeah, don't worry about the white light explosions. We know all about those. Don't worry about the disappearing tricks. We know all about those. And he said, great, tell me all about them. And they said, no, I mean, we don't understand them. We just know about them. We know that it happens, and that's where we're leaving it. You know, it happens. We don't want to understand it. We want to make fuel cells. Well, David wanted to understand it. It was then decided that since this stuff was going to be proven as the kind of material that could be used in fuel cells, they said you ought to get down to the patent office and lodge a patent on this. You know, you need to lodge it because somebody else could discover it and stop you from working with it. So that's what he did. And there's a portion in the application where you have to do tests with weights and measures. Well, the funny thing about this material was that they'd noticed that its weight was fluctuating. So he said, well, like when? You know, at what stage do we weigh it? They said, well, you're just going to have to keep heating it and cooling it and heating it and cooling it and seeing what the mean weight is. So they got this machine, which is called a thermogravimetric analyzer, and they started doing this weighing. Well, it was actually quite remarkable. They managed to get readings during heating that took it to a weight of less than 0. They managed to get readings during cooling that took it to anything up to 700 times its original weight. Think of the Alexandrian Paradise Stone. These powders will outweigh the original quantity of gold. They can also be lighter than a feather. That was exactly what it was doing. But during the process, there was one particular moment in time where the weight fell very quickly and very dramatically at that moment, and it fell by 44% suddenly. But what they noticed was something really odd, because the less than 0 weight that they were getting didn't make a lot of sense. It was sitting there in a pan in the lab on effectively weighing equipment. The pan itself weighs something. You have to compensate for it before you put the other material in it. But what they discovered was that it was reading all of these 0 weights, below 0, but they thought, well, what about the pan? That should weigh something. So they tipped the material out and put the pan back, and it suddenly weighed more without the material in it than it did when it was in it. This stuff was not only levitating, it was carrying the pan with it. And they learned that this stuff has the power to give levitational qualities to its host. So they carried on and they thought, well, we've got to do these other things for the application. We've got to see if it's conductive. That was the next test they had to do. So they put wires and electrodes into it, attached them to a voltmeter, turned on the power, nothing. And then they thought, well, it's got to be a conductor of some sort, because if it's capable of holding energy, you know, how are General Electric doing it? You know, it has to be conductive. Anyway, it turned out that it was a superconductor rather than a conductor. Superconductors are very, very strange animals. They don't need contacts to convey to each other. They convey to each other through resonant frequencies, through lights. The interesting thing is that if you transmit electricity from A to B with a wire, you always get some dispersion. You always lose some energy. With this, you lose nothing. 100% can go from there to there, no contact in between, 100% stays. It works so differently because it doesn't allow voltage potential to exist within itself. Neither does it allow any magnetic field to exist within itself. It's totally null. It doesn't react to North Pole, South Pole. It has its own quality, and its own quality defines all the laws. Here we have a standard magnet. We have North and South Pole. It's the magnet we all use. It will attract metals. And in fact, even if you put above it something that it won't attract, it'll fall down onto it because gravity will just take it there. That superconductor doesn't. Wants nothing to do with it. Won't be attracted by it, won't particularly be repelled by it, but it's just placed there above it and it'll just stay wherever it's put. We know that its anti-gravity properties can be translated to its host. We know that the scale of that doesn't seem to matter. It's macrocosm, microcosm, big, small, has nothing to do with these superconductors. So in as much as that tons of it would